Okay, thank you, Al. Let me move on and continue. My lecture today is mostly going to be about some theoretical aspects of matching market design, so that's an immense topic, and I'll only be able to touch on a couple of issues here. I want to start off by echoing one of the questions that Al started with, which is the very first question any design economist needs to confront, which is why do you need to design a market? And a very closely related question to that is what determines the set of instruments that you can use for designing markets? Or a question that sometimes matching market designers get, which is why can't you use prices here? And these are pretty fundamental questions that economic theorists have debated for decades, so I won't have time to do justice to them. But I do think it's helpful to set the stage by telling you a bit about one of my favorite design markets, and that is the Oklahoma land rush of 1889. So this was a system used in the late 1800s, devised by President Benjamin Harrison to allocate land parcels to settlers, non-native settlers in Oklahoma. The mechanism worked as follows. Settlers were asked to queue up on high noon of April 22nd. As soon as it was high noon, there was a race. Whoever got to a land parcel first was allowed to claim it. Okay, and now not everyone played by the rules. So some individuals jumped the queue. In fact, those individuals became known as Sooners, and some of you may have heard of the University of Oklahoma football team. They're called the Sooners. And as far as I know, no economist was involved in designing this market. But when we see a situation like this, it raises the question that many market designers start with: could we have designed a better system? And if you look at land parcel allocation, and following this, states like Georgia used a lottery. As far as I know, no state actually used an auction-based system. But there are many examples of markets that are designed by someone, and many examples where prices are not used. Some examples that may be familiar to labor economists in particular include forced conscription. So for a long time, the United States had a draft, despite Milton Friedman's urgings to get rid of the draft. Finally, that was eliminated. Gary Becker famously argued that green cards should be auctioned. That yet has not happened in the United States. So green cards are partly allocated by lottery, and I sure would wish that I could pay someone to serve on a jury rather than serve myself. So why is it that we don't use prices in some of these settings? And there are many reasons. So one basic trade-off is the trade-off between the willingness to pay and the ability to pay. So price-based allocation has the benefit of allowing people to express their preferences, but if a market-based price is used, then income plays a large role. Rationing or lottery-based systems may allow true needs to be met. So there could be an equity or fairness rationale for using a lottery rather than a price. The problems include over-delivery to those who do not really value items. So this is an old idea, first formalized by Marty Weitzman. It's been refined by a number of authors when there's resale markets, when the set of instruments is more complicated. But this is one common reason why we don't see price-based allocation. Now, more generally, why have we restricted the set of instruments? There's often technological constraints. Contracts cannot be made rich enough. There's enforcement constraints. There are also moral or repugnance constraints. These are fluid things. And so what I want to do in my talk today is acknowledge that we like prices as much as any other economist, but start from a position where we realize that they are not or sometimes cannot be used. So the goal today is to give you a whirlwind tour of some of the canonical ideas in matching market design. Okay, so I'm going to start off talking about a class of environments that we call the one-sided matching environment, simply allocating objects. And in that environment, I'm going to introduce two big ideas. First is what we call a serial dictatorship. And the second big idea is Gale's top trading cycles. Then we'll move on to talk about two-sided matching environments. And I'll quickly review the deferred acceptance literature that Al described. and talk about the Boston mechanism and some of the variants that we've seen in the field. And then, depending on how much time we have, I'll talk about a couple of new issues, design issues, designing choice functions, and I'll conclude by telling you a little bit about some developments where deferred acceptance has been generalized to actually include richer commodities, prices, or even contracts. And this is a very active theoretical frontier. So let's get started. Okay, so the first model I want to introduce is what's called a house allocation problem. Okay, so many of these models are parables of big decisions in one's life: housing, the marriage model, college admissions. So what happens in the housing model? There's a finite set of houses. Okay, there's a finite set of agents. In the model, we only work with ordinal preferences. Okay, so agents have strict preferences over houses. And an allocation in this setting is simply a matching. Okay, so that is a function that specifies each agent's assignment such that no house is assigned to more than one agent. Okay, so this is what we get to start with. Now, with these primitives in hand, what are some things we could potentially do? A natural thing to do is what's called a serial dictatorship. Okay, so given an ordering of agents, in a serial dictatorship, the first agent will be assigned his top choice. The next agent is assigned his top choice among the remaining houses, so on and so forth. Okay, this is like a queue. Okay, it's a dictatorship because when it's your turn, you are the dictator, you get to choose, and it's serial because we're processing agents according to this ordering. And this mechanism has some very nice properties. Okay, the first property is this is a strategy-proof mechanism. What does that mean? That means truth-telling is a weakly dominant strategy for all participants. Now, it's worth pointing out that it's not that easy to find strategy-proof mechanisms. In fact, we have very strong results saying, in general, we don't have many dominant strategy mechanisms. So when we restrict the environment such that agents have preferences only over houses, not over what other people got, it is possible to find strategy-proof mechanisms in practice. So why is it strategy-proof? Well, when it's your turn, the best thing you can do is say the house that you want the most among what's available. And you cannot influence when it's your turn because the ordering is given. The other property of this mechanism is Pareto efficiency. So this is Pareto efficient. That is, there is no other allocation where an individual is doing strictly better and no individual is doing worse. Okay? So this is as simple as it gets. Okay? Now, what's a problem with this mechanism? Well, a problem with this mechanism is the ordering determines everything. Okay? If I'm the last person in line, I only get to pick among what's left over. More formally, we can say this mechanism doesn't satisfy a property known as the equal treatment of equals. That is, if two individuals have the same preferences, they should get the same allocation. Okay? So that can be seen as a fairness consideration. And in this setting, the only way you can satisfy equal treatment of equals is by using some kind of random or stochastic mechanism. So how would we enrich this mechanism to make it random so that we could have two individuals with the same preferences getting the same outcome? Well, we could do that by simply using a lottery, a uniform lottery, to determine the ordering. Okay? And that's what's known as a random serial dictatorship. Okay? So a random serial dictatorship inherits the properties of a serial dictatorship. It's also strategy-proof, and it's ex post Pareto efficient. Okay, so far so good. So this is as simple as it gets. Now let's make this a little bit more complicated by adding endowments to the problem. Okay, so now here's the jargon. So in the house allocation problem, there are no endowments. So the objects are collectively owned by everyone. In a housing market problem, we'll consider the same exact environment, but our starting point is individuals enter with a house. Okay? So you can imagine, and this is a great tool for some of the students in first-year micro, this is the simplest possible exchange economy. Every agent has an endowment of a house. Agents have strict preferences. And once we introduce this idea of endowments, it motivates thinking about a couple of other properties. So the next property I want to introduce is individual rationality. So that is what it sounds like. So an allocation is individually rational if each agent is doing at least as well as his endowment. Okay? And then the core property. Okay? The core property Allocation is a core allocation if there's no coalition of agents who would prefer to contract amongst themselves compared to what they get in the allocation. Okay, so in the limit, since we can consider any size coalition, if it's a coalition of one individual, asking an allocation to be in the core is the same thing as saying it's individually rational. If the coalition was everyone, it's the same thing as Pareto efficiency. Okay, so the core is a central concept in this literature. So we have endowments. Now, how are we going to clear this market? And that leads to one of the very prominent mechanisms in the literature here, and this is Gale's top trading cycles algorithm. Okay, so in fact, this was described in an article not written by Gale. It was in Shapley and Scarf's article in 1974. So how does this work? So in step one, each agent points to the owner of his favorite house. Since the problem is finite, there's going to be at least one cycle. A cycle is an agent pointing to another agent that eventually points back to the initiating agent. And once we find a cycle, each agent in a cycle is assigned the house of the agent he points to, and he's removed from the market. So we execute that trade. Okay? If there's at least one remaining agent, we'll go on to the next step. Okay? So we've looked for a top cycle, okay, top choices, and we have the agents who are in the cycle trade amongst themselves. If you're left over in the generic step, you point to your favorite house that remains. Okay. Again, because the problem is finite, there will be a cycle, an agent pointing to another agent, so on and so forth. We remove the cycle. Now, in any step, there can be more than one cycle, but each agent can only be part of one cycle. We execute those trades, and we iterate. Okay? So this is Gale's top trading cycles. Okay? Now, this is a canonical mechanism because it has a number of fantastic properties. Okay? So what are those properties? First, the outcome of top trading cycles is the unique core matching in this environment with individuals and houses. And it's also the unique competitive equilibrium allocation. Okay, so we can construct a price vector to decentralize this allocation. And so that was one of the first results about this mechanism. The second result is we can think of the core top trading cycles as a direct mechanism, and by that I mean it's a preference revelation mechanism. Individuals reveal their type, and it is a strategy-proof mechanism. Okay, so here now is a second example where we have found a dominant strategy mechanism. You cannot influence what you get by submitting a false report of what houses you want. Okay? And loosely speaking there, you can't influence which cycles form, so you might as well report which houses you want correctly, because the cycles that form will, the cycle in which you're involved will be the one that gives you the best house you can achieve. The third result now is a bit of a specialist result, but it says that this mechanism for this environment is the only mechanism you can use if you're interested in Pareto efficiency, individual rationality, and strategy proofness. Okay? So the case is sealed, you could say. We have an ideal mechanism, great incentives, great efficiency properties. There's nothing else you can do. Okay? Now, these results are kind of classic results, but this mechanism has inspired some more recent literature by thinking of the following kind of extension. Okay? So let's imagine a hybrid scenario where not all agents have endowments. Okay? There may be some agents who come to the problem owning a house, and there's some agents who are newcomers. Okay? Or we can think of a scenario where instead of having endowments, individuals start with property rights. Okay? I have a property right over Pat for a given house because I'm older than Pat, say. Or I've scored higher on a test than Pat, or I have a better lottery draw than Pat. Okay? So you can think of that kind of like an endowment, but it's probably more appropriate to think of this like a property right. So in this kind of environment, when we have these property rights or these priorities, we can adapt top trading cycles by this following modification. In the original version, I said you point to the owner of the house that you want the most. Now instead, why don't you point to the house that you want the most, and the house, or the object in this case, will point to the agent who's got the highest property right. Okay, so that's a very modest modification, but it allows us to accommodate a richer set of problems. Okay? Now, the reason I'm telling you about these old ideas is that this mechanism was actually used in practice, as far as I know, for the first time to allocate children to school in New Orleans. Okay, so the Recovery School District used a version of top trading cycles to allocate children to school, to both traditional public schools and charter schools. And so here's how this was described to the public. Okay, so this is a clip of the algorithm in the Times-Picayune. Okay, so that's the now defunct newspaper in New Orleans. In scenario A, we have a cycle involving just one person. So here, student 1 is pointing to school A, his top choice, and the school is pointing to the student. Okay, so a cycle can involve just one kid. Cycles can involve more than one kid, of course. So here's an example of scenario B. Student 1 is pointing to school B. School B's the student who's got the highest claim, the highest property right there is student 2, so that's why the school points to 2. 2 then says my first choice is school C, so he's pointing to school C. C gives 3 the highest priority. 3 in turn wants school A. So we've found this trade. We execute that trade by assigning the child to the school that they're pointing to. Okay. So the mechanism in the RSD is Pareto efficient, and it's also strategy proof. Okay. So that's the class of one-sided matching models. Okay, 2 big ideas: serial dictatorships and Gale's top trading cycles. Now let's enrich the environment and think about matching 2 sides. Okay, so this is closer to what Al was talking about. So here, what's the jargon? Okay, so we have house allocation, that's one-sided. We have the marriage problem. Okay, that's a fable of matching together men and women. What's key about the marriage problem is it's a one-to-one matching problem. Okay, so we can't assign one man to more than one woman, and vice versa. So that's what we call the marriage problem. College admissions is a scenario where it's a many-to-one matching problem. Okay, so the jargon there is it's many because a college could have many seats. Okay, and the key concept. So Al has already introduced the celebrated deferred acceptance algorithm. And stability. Stability in this context is individual rationality plus the absence of a pairwise block. Okay. Now, the literature on deferred acceptance is by now immense. So I looked at my undergraduate class lecture notes and said, what are the most important results that someone would need to know about deferred acceptance? Okay. And so I've summarized them here. So the first result is what we call side optimality. So there is a worker optimal stable matching and there is a firm optimal stable matching. So Al mentioned that already. And indeed, if I look at the worker optimal stable matching, that's the best for workers, but it's also firm pessimal. So that's the worst for firms. And vice versa. If I look at the firm optimal stable matching, that's the worst stable matching for workers. So that's what some people call the opposing interests or conflict between the 2 sides of the market here. Okay. The second result that's important is the incentive result. So we have a dominant strategy mechanism, but in this case, you have to restrict the set of agents. So if we think about the deferred acceptance algorithm where workers propose to firms, that version is a dominant strategy mechanism. It's strategy proof for workers. Okay. If we were to ask, do we have a way to implement a stable allocation that's strategy proof for both sides? The answer is no. So there's no way to do that unless we think about approximations like Al mentioned, large market approximations. The third result, okay, now again there's a little bit of jargon here, is what people call the rural hospitals result. Okay, so what is the rural hospitals result? That's a result that says something of the following sort. Across all stable matchings, the set of agents who are matched is the same. Okay, now why would you ever call this rural hospitals? Well, one story about this is there's a long-standing concern that there's not enough doctors working in rural areas in the United States. Okay, and one might have said, well, is that because of the match, the fact that they're using a stable matching algorithm? Well, thanks to the rural hospitals theorem, we know if you have a rural hospital that has an empty seat that no one wanted to go there, it didn't matter which of the different stable points you chose in practice. You would always have that hospital not have everyone taking a seat at that place. So that's why I think one reason people call this a rural hospitals result. Okay. Fourth result, okay, this is a result that I'm calling order independence. Okay, so the way deferred acceptance is usually described is what Al did. He said everyone proposes, all workers propose to firms simultaneously. But in practice, we don't need simultaneous proposals. With deferred acceptance, we can do this in an iterative way. And in fact, the sequence of proposals that are made does not matter what the order is. We'll always get the same outcome. Okay, so take a given worker, have him propose to his first choice. If he's rejected there, we could go back to him and have him propose to a second choice. We don't need to wait to see what happens to all the other workers. Okay? And the reason we can do that is because this is a deferred process. Nothing is finalized until the very end.